Alright, let's look at the a couple of indeterminate forms. Alright, so first one, 0 times infinity. Alright, so if let x go to infinity, you can see that this first guy, of course, goes to infinity. Right, but as x approaches infinity, pi over infinity, pi over x, this guy approaches 0. Right? Sine of 0 is 0, so sine approaches 0. Right? So you have a 0 times the infinity situation. So what we can do is we can rewrite this guy as, so this, you have a limit as x approaches infinity. Right? So instead of x, I'm going to write it as 1 over x, right? Which is the same thing, right? So so you have sine of pi over x, right? Right. If you rewrite that, you can see that this is going to be a 0 over 0 situation. So 1 over infinity, so this approaches 0. Right? Again, sine of 0 approaches 0. Right? So this is a perfect setup for L'Hopital's rule. So let's apply L'Hopital's rule. So by applying L'Hopital's rule, we're going to get this. So you still have the limit as x approaches infinity. Right? So derivative of the top would be, so you have a cosine. Right, then leave the inside function as it is, right, multiply by derivative of the inside. So derivative of inside would be negative, pi is just a constant, over, so it's a negative 1 power, so it's negative 2 powers, so x squared on the bottom, right? And the same thing happens with the bottom, it's just a negative 1 over x squared. Right, so we took the derivative of the top and took the derivative of the bottom separately. We get this. All right, then we can actually cancel negative 1 over x squared. Cancel with, there's a negative 1 over x squared. There's going to be pi left over there. All right, so what you get is really, all right, so x goes to infinity, so pi over x goes to 0. So you have a cosine of 0, which is 1. Times, this is just going to be pi, so 1 times pi, so it's going to be pi. So the limit of the limit we're looking for is pi for that guy. Alright, so another indeterminate form would be infinity minus infinity. So what would you get if you subtract infinity from infinity? So we can't really make a decision from here. So here, you can see that as x goes to infinity, so of course x approaches infinity, so this is going to be infinity minus natural log of infinity is still infinity. So we have that. So somehow we want to make it look like 0 over 0 or infinity over infinity. Alright, so let's try this. I'm going to rewrite x in terms of natural log. So here you have limit x approaches infinity. Right? So we can rewrite x as natural log of e to the x. Right? Remember, exponential function and log functions are inverses of each other, so they basically cancel each other out. So you're just going to get x. Right? So minus natural log of x. Right? Then we can use the log property. If you have a subtraction outside, we can write it as a single log, but it's going to be division inside. So we can write it as limit as x approaches infinity. It's a natural log of e to the x divided by x. All right. Then we can squeeze the limit inside the natural log, because natural log is a continuous function. So we can have you have a natural log then you have a limit as x approaches infinity, e to the x over x, right? So we can write it like that, right? Then again, you have this perfect situation for this is in this case e to the infinity goes to infinity and x approaches infinity, right? So now we have an infinity over infinity situation, so we can apply the L'Hopital's rule, right? So by applying L'Hopital's rule, we'll get limit, right? Natural log, right? Then you still have limit as x approaches infinity, right? Derivative of e to the x is actually itself, and derivative of x is 1, right? Then as x approaches infinity, e to the infinity is going to go to, e to the x is going to go to infinity, right? So you have natural log of infinity is still going to be infinity, right? So that's the limit for the second limit when you have infinity minus infinity. All right, that's it. I hope that this was clear.